अस्सलाम वालेकुम, वेलकम बैक टू मैथमेटिकल मेथड्स ऑफ फिज़िक्स। आज हम इसका लेक्चर नंबर 3 पढ़ेंगे। सबसे पहले हम देखते हैं कि लास्ट लेक्चर में हमने क्या किया था। सो वी हैव स्टडीड द फॉर्मेशन ऑफ वोल्टेरा इंटीग्रल इक्वेशन, formation of Fredholm integral equation, solution of an integral equation. In these three topics, we considered, in the first one, we considered initial value problem from differential equations, and we solved it to obtain the Volterra type integral equation. Similarly, we considered a boundary value problem, a second order equation with the boundary conditions, integrated them twice, and we got the Fredholm integral equations. And then we saw how to verify a function to be a solution of integral equation. So this was our last lecture, lecture number 2. Today in lecture number 3, we will be studying the method of successive approximations. Volterra integral equation, Fredholm integral equation. Again, because these are the two basic type of integral equations, so whatever we are studying, we implement that on these two equations. And then we will see some examples. Method of successive approximation. First we will apply this to Volterra integral equation. Let us consider a Volterra integral equation of the second kind. And now you are familiar with the Volterra integral equation because it's our third lecture and we are considering this equation again and again. Ux equal to fx plus lambda a to x kx xi uxi dxi, right? This is our Volterra equation. Well, why Volterra? Because limits of integrations are from a to x. All right, where kxt and fx are both continuous functions. In the method of successive approximations, we replace the unknown function ux under the integral sign by any selective real valued continuous function u naught x. We select a function u naught x and we replace this because only problem in our equation is ux is coming inside the integral and we don't know what to do, right? So what we do is we replace it with some selective function u naught of x and we solve the right hand side to obtain ux. We call that u1 of x. All right, so this is called the 0th approximation. The best choices for u naught of x are 0, 1 and x. Right? Of course, we want to keep things easier. So we don't want to keep u naught x to be a very complicated function. Why should we do that? It's a very first approximation, 0th order approximation. We call it 0, 1 or x. All right? You can choose something else as well. It's not restricted to these three functions. But these are the best choices basically. This substitution will give the first approximation u1x by this formula. You see, on the right hand side, we replaced u of xi with the function u0 of xi. When we do that and solve it, we get ux, but we don't call it ux, we call it u1 of x. So this is our first order approximation now. From u and rx, you got u1x. Now from u1x, you will get u2x. Here u1x is continuous because k, f and u naught all are continuous. If this is a continuous function, then we will find the second approximation by replacing u naught by u1. So what you got u1, you replace u naught by u1 now and solve the right hand side, get u2 of x. You see, u2 of x is coming from u1 of x. All right. So following the same procedure, we obtain an infinite sequence of functions u naught, u1, u2 up to un. All right, that satisfies the recurrence relation, this one, because you see we took u0, it gave me u1 here. We replaced u1 here, it gave us u2. u2 gave us u3, so on. So it is true for any n. If I replace n minus n here, it will give me un here for n is equal to 1, 2, 3, 4, 5. Right? So this is your recurrence relation. Thus, at the limit, the solution ux of the integral equation is this one. If we take the limit on both sides, then this is a sequence which is converging to a function ux, then this will converge to ux, this will converge to ux. All right, so you get the integral equation. It means you are getting a sequence of functions. The limit of that sequence will be the solution of integral equation. So this is the method of successive approximation to solve an integral equation. All right, so ux is the limit of those sequence. So this is your solution. So it means here you can see the last formula, this formula tells us that the solution is independent of initial guess u naught x. So what your initial guess was, your solution is not depending on that. So whatever your guess is, if you get a convergent sequence, you will get a solution. You start from 0, you start from 1, you start from x, whatever. If you are getting a sequence and that converges to a function u of x, then you got the solution. You don't have to worry about u naught x. However, if we follow Picard's process of successive approximation, then we need to set u naught x is equal to f of x. So Picard suggested that why you look for different u naught x, maybe sometimes it will give you convergent sequence, and maybe it don't give you convergent sequence for some choices. So he suggested that start with the function f of x. Start with the function f of x, which is appearing here, you see, which is appearing in your integral equation. Take that fx to be your u naught x. This will give you a convergent sequence all the time. All right, so this is Picard's process. So in the method of successive approximation. So if we pick u naught x is equal to f of x, then this is your first approximation. Right? This is your first approximation. You replaced u naught xi with f of xi, which is the same as this one. All right. Similarly, u1 will give you u2, u2 give you u3, and so on. So this is your un minus 1, and this is your un. All the remaining process is the same. The method of successive approximation is the same. Only difference in Picard's process is that you started with f of xi. That's it. Remaining everything is the same. All the procedure is the same. All right. Now here, if you take the difference between these two approximations, let's say u1 minus u naught, right? You want to find the error. That how much is the error? You took the first guess as u naught, you updated it to u1. There will be some difference between u naught and u1. So we are calculating that. If we calculate this one by just replacing, this is the function, this is u1, this is u naught. All right. fx and fx are cancelled out. You got this one. u2 minus u1 gives you this. All right, which is this. If you simplify, this is u2, this is u naught, u1. All right, this is u2, this is u1. You subtracted it, fx and fx are cancelled out again. You took lambda as common, so you got these two things. Right, fxi plus u1 xi. All right, so here we replace the value of u1 as well. What is u1? u1 is this whole thing. What is u1? u1 is this whole thing. So we replace this u1 by this whole thing. All right, minus lambda times this one. All right, so by simplifying you got this. It's very easy, just straightforward calculations. Straightforward calculations. In this term, all you are seeing is that here kx xi u1 xi. So we replace this u1 xi by this term. This is u1, and this remains as it is. Now because kxi is common in both, if you subtract fxi will cancel each other again, and you are left with this integral. That's why Picard's process is famous, just because every time this fx cancels out, and you are left with a simpler form of your difference, right? So interchanging the order of integration, if you change the order of integration on the right hand side, we obtain this one. We change the order of integration, we get this one, and by simplifying, because a to x, eta to x, and these are the kernels, right? So we can call it, because this, see here there is no f or there is no y. So this is a function of x and xi. See, you are integrating with respect to xi. So xi is gone. So you will be left with x and eta. So x and eta will give you another kernel. So you got k2x, this is another kernel, all right, where k2x x eta is coming from the first kernel k. K kernel is given, you got k2. Similarly, if you take the difference between u3 and u2, you will end up getting k3, lambda cube k3, where k3 is given by this one. All the time you replace with this k, k2, k, k3, k, k4 will give you the next kernels, right? So general relationship is like that. The difference is this one, where kn is given by k times kn minus 2. Kn is given by k times kn minus 1, all right? So that's how you update your kernels at each step as well. Again, writing all the differences we have: first difference, second difference, third difference, and the last difference. All right. So in first difference, you see you have just k. The second one k2, k3, so on up to kn. All right. If you add all these equations, what will happen? u1 will cancel out, u2 will cancel out, u3 cancels out, un minus 1 will cancel out. You will be left with just un and u0. On the left hand side, you will be left with just un and u0. So if you do that, you're left with un and u0, and right hand side you can just add all these up. By adding all these up, and you can write just one integral, right? If you want to write just one integral, you can write it like that. The one integration is lambda k, lambda square k2, lambda cube k3, and so on, lambda n kn times of eta d eta. All right. So you got this summation form. Because power of the lambda is increasing, so lambda to the power n, and subscript of the k is also increasing, so kn. Lambda k1, lambda square k2, lambda cube k3, and so on. You can add them up from 1 to n. So this is what you got. This is another integral type equation. You see un of x is u0 of x plus this. We brought just this u0 x on the right hand side and wrote this equation again. So if you substitute the value u0 x, what was our u0 x? It was f of x. शुरू में हमने u0 क्या लिया था? fx. पिकार्ड्स प्रोसेस में हमने fx लिया था. तो अगर हम fx ये u0 x को replace कर दें with fx, तो this is what you got. So see, this is un. Now if you take the limit, from previous discussion we know that the solution of the integral equation is this. It's not just un of x. The solution is the limit of un of x. So if you take the limit of as n goes to infinity, you get this one. Limit of this will give you u, because when you take the limit n goes to infinity, you call it u of x. Fx will remain fx, nothing is happening. But here, if you take the limit as n goes to infinity, then this will become infinity. You see here, if n goes to infinity, then this power m goes from 1 to n, but now m will go from 1 to infinity because you have taken n to be infinity. So this is called the resolvent kernel. All right, this is called the resolvent kernel. You got lambda m minus 1 km. This should be lambda m km, and so on from 1 to infinity. We call it resolvent kernel. Lambda, x, eta, and lambda. You see, or x, it depends on x, it depends on eta, it depends on lambda. All right. In last lecture, we gave you the definition of resolvent kernel, and I told you at that time, I think it was in very first lecture. In first lecture, I gave you the example of resolvent kernel, and I said, don't worry about how we got the solution. We said, if this is the solution, this is called the resolvent kernel, and now you see you have the proof of that thing. If you go back to the first lecture and see at the last slides, resolvent kernel, I said, assume that the integral equation has this type of solution, then this is called the resolvent kernel. And now you have the background, the motivation, how you got this resolvent kernel basically. So the background idea is method of successive approximations. All right. So if you implement method of successive approximation, you will get the resolvent kernel. So we did this for Volterra integral equation. Now let's move on to the Fredholm integral equation. All right, let's move on to Fredholm integral equation. Solution of Fredholm integral equation by successive approximations. The successive approximation method, which was applied to Volterra integral equations of the second kind, can be applied even more easily to the basic Fredholm integral equations of the second kind. So if you write the Fredholm integral equation, what is the difference? Difference is limits of integration are from a to b. If we set u naught x is equal to f of x, then this method is also known as Picard's method. Again, if the first approximation is f of x, we call it Picard's method. With this first approximation becomes u1 of x is equal to fx plus lambda a to b kx eta f eta d eta, because the first u naught x is f eta. I replaced u naught x by x eta. The second approximation is u2 of x, and u2 of x is coming from u1 of x. Right? Again, if I replace u1 by u2, you will get u3. u3 will give you u4, and so on. It's iterative method. It's successive approximation. All right? So you got un as this one, because n will come from n minus 1. So here, u1 of x is equal to fx plus lambda a to b kx eta u naught eta d eta. Because we are integrating with respect to eta, and the limits are constants here. If you replace eta by x, you will get a function of x. So you may write, for convenience, you may write this as a function of x, psi1 of x, where psi1x is this integration, because this integration is a function of x. The second approximation, u2, can be obtained as this. So if you replace u1 eta by this one, we get this one, right? So here again, if we simplify it, what you get is f eta kx eta gives, this is the same thing, fx eta kx eta, this is psi1 of x. But when this multiplied with psi1 of x, this is lambda square. All right, lambda square psi2 of x. So I call k, when k multiplied by psi1 of eta, it gives you psi2 of eta. Right? So proceeding in this manner, the final solution ux can be obtained as this one, because the first one was u1 is fx plus lambda psi1, u2 is fx plus psi1 plus lambda square psi2, and similarly ux will be fx plus psi1 plus lambda square psi2 plus lambda cube psi3 plus lambda 4 psi4, and so on up to lambda and phi n, and so on. So your fx will be fx plus summation n goes from 1 to infinity, lambda n psi n of x. This is a series, this is an infinite series. You see, this is infinite series where psi1 and psi2 are coming from the kernels. It's not just any, they are not just any functions. They are coming from the kernels. You see, psi1 comes from f eta. If any function and kernel is given, you got this psi1. Now you replaced f by psi1 to get psi2 is here, psi1. And now you replace psi1 to psi2, you will get psi3, so on. And right? So this series is a special series, and it's called a Neumann series. Right? It's an infinite series, but it's a special series coming from kernels and f of x. So that's why it's Neumann basically gave that series. So we call this Neumann series. All right, where phi n of x is coming from the kernels. You see. All right, and this is again they are coming successively from the previous ones. Psi1 gives you psi2, psi2 gives you psi3, and so on. This is the same method as we discussed in Volterra integral equation. Construct the resolvent kernel for the Fredholm integral equation. A little exercise for you. It's really not a problem, because you have to follow the same steps basically, and how to find. You got the solution, right? But you need to find the resolvent kernel. How to find the resolvent kernel? So resolvent kernel will come from this series. All right. If you replace these integral signs here and write this series in terms of kx eta, all right, that kx eta will give you the resolvent kernel. All right. So it's a little exercise for you. Just try it out. Hopefully you will get it. So let's see some examples now. We have seen method of successive approximations for Volterra and Fredholm integral equations for both of them. So let's see how we can implement these examples to these methods to some examples. So these are examples. I'll do one by one by hand. So your example is ux is equal to fx plus lambda 0 to 1 e to the power x minus xi y xi dxi. This is u of xi. Alright, so this is your Fredholm integral equation. Kernel is e to the x minus xi. This is your kernel. We have to implement the method of successive approximation. Alright, so here your kernel is e to the power x minus xi. This is your kernel. Alright. So what is K1? We have to find that resolvent kernel. So Kx xi is equal to K. The first one is the given one, K. K is e to the x. This is, here we are starting. So K2 comes from K1, right? K2 is 0 to 1 Kx xi and K1 xxi dxi. Right? This is your t xi, and this is t. Because this is a function of x and xi, so you have to start with xt and t xi. T is a dummy variable; it will be gone after the integration, and you will be left with x and xi. All right. So this is your first one. So if you find out K2, you will get Kxt is x minus xi, sorry, x minus t times K1 is again same, e to the t minus xi dt. So now if you integrate, this is x minus xi dt. T and t will be cancelled. So you got x minus xi, and x minus xi is free of t. So you got e to the x minus xi 0 to 1 dt, which is 1. So you got e to the x minus xi. This is your second kernel. Third one will be, if I take K3 xxi, K3 xxi will be 0 to 1 k of xt and K2 of txi dt. Right? If I replace K2, it will give me K3. And nothing changed because K2 is again the same. You see, K1, K2 are the same. So if I replace, I will get again, it will give me again x minus xi, the same thing. Right? So here we are getting exactly same thing all the time. All right. So on. If we generalize, what will be our K m xxi? This will be same, e to the x minus xi. I'm getting the same kernel back. So this is what we got for all m goes from 1, 2, 3, and so on. Now the resolvent kernel is, your resolvent kernel have this form, or x xi and lambda. This is your summation m goes from 1 to infinity lambda m minus 1 k m x xi. Right? This is the formula for the resolvent kernel, and resolvent kernel gives you lambda summation m 1 to infinity lambda m minus 1, and our kernels km are all x minus xi. Right? So basically e to the x minus xi is common. This is common, and you are getting 1 plus lambda square plus so on. Right? So what is this? 1 plus lambda square plus so on. This series is 1 over 1 minus lambda. This is the series of 1 over 1 minus lambda. Right? So your resolvent kernel came out to be So therefore, your resolvent kernel kx xi lambda has this form, e to the power x minus xi, and series became 1 over 1 minus lambda. So this is nothing but e to the x minus xi divided by 1 minus lambda. So this is your resolvent kernel for the given Fredholm integral equation. All right. Now what will be the solution then? And if you recall the series, this series which is 1 over 1 minus lambda is equal to 1 plus lambda square plus so on. This converges to this function only if lambda is less than 1, right? So this is the condition we need to put. So what is the solution then? So therefore, finally, the solution of the given integral equation is, what was the solution? U of x is equal to fx plus lambda 0 to 1 resolvent kernel times f xi dxi, right? This is your solution, right? This is the solution of your integral equation. So if you want to integrate, you can do it. Let's say your resolvent kernel is e to the x minus xi over 1 minus lambda times f xi dxi, right? So that's how you will get. 1 over lambda is common, you can bring it out and integrate. This is a constant that can be brought out. So if fx is given to you, then you can integrate and find the final answer, right? So if fx is given to you, you can replace it here, integrate it, and get the answer. So this is the solution of your integral equation by using method of successive approximation. All right. So we found the solution of this first equation, ux equal to fx plus lambda 0 to x e to the x minus eta u eta d eta. All right. So this was very easy because the kernels we were getting the same kernels every time. All right. So again, you can do more. You can solve the same equation with these kernels as well. Replace this e to the x minus eta by x minus eta and see what happens. These are 3 examples, and I hope you can do them. Let me solve one of them for you guys. So these are 3 examples. Let me try this one, the last one. Kx eta 2 plus cosine x 2 plus cosine eta. All right. So with this one, let's see how the things change. So let's say this is your equation now with, let's do it with Volterra equation. 0 to x k x xi u xi dxi. This is Volterra differential equation, integral equation, where fx and kx are given, where fx is ex sine x, let's say this one, and kernel is given as 2 plus cosine x over 2 plus cosine xi. All right. So let's say this is a Volterra integral equation with fx and kernel given to you. So we need to use method of successive approximation to solve this. So let's do it. First of all, what we need? We need the resolvent kernel. So what is your k1? K1 x xi is equal to 0 to x k x t k t xi dt, right? This was your formula for the first approximation of the kernel. All right. And this is from t to x, not xi to x. T goes from xi to x. All right. So this is your formula. So if we replace the values, kxt is 2 plus cosine x, 2 plus cosine t, because we are writing for xt now. So xi will be replaced by t. And then we are writing for t xi as well. So 2 plus cosine t and 2 plus cosine xi. You have to be very careful. It's not the square. It's not the square because here xt and t xi. So xt and then t xi. Right? So you have to be very careful. So now you see this 2t are cancelled. Right? So you are left with xi to x, 2 plus cosine x over 2 plus cosine xi dxi. You are integrating with respect to xi, so 2 plus cosine x is constant for that one. So your integration will depend only on 2 plus cosine xi. This is, we are integrating with respect to t, you see, with respect to t. And there is no t inside anymore. T is gone. So what you got is 2 plus cosine x, 2 plus cosine xi, this is common, and integral is just t from xi to x. So this will become xi minus x. So your k1 is, so your k1 x xi is 2 plus cosine x over 2 plus cosine xi times x minus xi. So this is your first one, k1xt. We call it k2, not k1, right? Another mistake. Not a mistake. Here it's k2, which is k1, and k1 is the same as k. So this is k2. We got k2 here, and now k3 will be, k3x xi will be from xi to x, kxt and k2 txi, right, dt. So k2. So now it's from xi to x. Kxt is just 2 plus cos x over 2 plus cos t. And what is kt2t? This one, k2 txi. K2 txi is 2 plus cos t over 2 plus cos xi times t minus xi dt, because you are replacing x by t here. So again this is gone, this is constant, you can bring it out. 2 plus cos x and 2 plus cos xi are constants, you can bring it out. So all you are left with is this one, t minus xi dt. So t minus xi with respect to t gives you t minus xi square by 2. So you got 2 plus cosine x over 2 plus cosine xi, and this is t minus xi square by 2. Right? Similarly, the next one will be t minus xi cube by 3, xi 4 by 4, and so on. All right? So if we carry on, your kn xt or km xi will be, because 2 plus cos x is common everywhere, 2 plus cosine xi is common everywhere. Here you are getting t minus x minus xi power for 2. It's x, not t. Right? So x minus xi square by 2 factorial is coming for 3. So it's 1 less. So this will be m minus 1 over m minus 1 factorial. All right? This will be your kernel. Yes, this is your kernel. So now resolvent kernel will be, what will be your resolvent kernel? So resolvent kernel is r x xi lambda is equal to summation m goes from 1 to infinity lambda m minus 1 k m x xi. So we just found the value of k m x xi. You can bring it out. So that is k1 x xi plus lambda k2 x xi plus lambda square k3 x xi and so on, plus lambda n k lambda n minus 1 k n x xi and plus so on. All right, this is what you are getting. So if you replace the values here, if by replacing the values, you can see r x xi lambda is nothing but 2 plus cosine x over 2 plus cosine xi. This is common, so 1 plus x minus xi plus x minus xi squared by 2 factorial plus so on, x minus xi n by n factorial minus 1, n minus 1, n minus 1 factorial. All right, and we have lambda as well. Here it's lambda square, it's lambda n minus 1. So this is what you are getting. All right, so again you can, I guess, write the compact form. This is nothing but, if you recall, this is the Maclaurin series of e to the power lambda x minus xi. Right? If you recall, e to the x is 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus so on. Right? So this is, what is x? X is this whole thing, and square of this whole thing, and power. Right? So x is lambda x minus xi in our case. Right? So in our case, this x is lambda x minus xi. That's why we got e to the power lambda x minus xi. So this is our resolvent kernel. All right, so this is our resolvent kernel, and once you have found the resolvent kernel, you can write the solution of the integral equation very easily. All right, so therefore the solution of integral equation is u of x is equal to fx plus lambda 0 to x, a resolvent kernel, times f xi d. All right, so that's how you can find the solution. Replace the resolvent kernel here, the values of x here, and you get the solution. So I guess we had fx here, right? F was given to x. F was ex sine x. So if you replace ex sine x here and replace the value of the kernel, simplify it, you will get the solution. I write you the final answer because this is not a difficult task to do. You just need to integrate a function, and the answer you will be getting is ex sine x. This is your fx plus the answer for the integration, you will get minus ex 2 plus cosine x natural log of 2 plus cosine x by 3. So just verify that whether you are getting this or not. It's not difficult. Your resolvent kernel is given, function is given. You just need to integrate and find this one. All right, so you can of course integrate and find this one. It's a very simple verification. So this is a solution of Volterra and equation by method of successive approximation. One last example, I guess this is another Fredholm equation, right? Following integral equation by the method of successive approximation. So let's see this equation as well. This is a Fredholm integral equation. So another example, it's a Fredholm type differential equation, an integral equation, uxt 5x by 6, so this is your function, plus 1 by 2. Lambda is basically fixed at 1 by 2 here. Lambda is not a parameter anymore. So xt and ut dt. All right. If you want, you can write xi as well. We have been writing xi. So maybe you just write xi. X xi, u xi, d xi. Let's say this is, because we have been writing xi. So this is our kernel here. This is our kernel. All right. Now, what is our k1xt? K1xxi is kxxi, right, which is xxi. First one is the same. For k2xxi, I need 0 to 1 kxt k1t xi dt. Right? So this is the formula, which is very well-known formula now. So if you do this, you will get 0 to 1. What is kxt? This is kxxi, which is xxi. So kxt will be xt. And then txi will be txi. dt. So xxi is common. T square has t cubed by 3 from 0 to 1. So it is 1 by 3. So xxi by 3. Right? This is your k2. It's k2. Now k3. K3xxi will be 0 to 1. Fredholm is easier than Volterra basically because your limits are constant, not variable. So this is kxt k2 txi dt. So this will be kxt is xt and k2 txi is txi by 3, right? See, k2 was xi t, but now we have to write txi, so it's txi by 3. So xxi by 3 is common now, and inside is t square, so it's again t cubed by 3 from 0 to 1. It is 1 by 3. So xxi by 3 square. All right. Similarly, if you find k4xxi, you will get 0 to 1 kxt k3 txi dt, which is 0 to 1 xt txi by 3 square dt. This will become xxi over 3 cube. Right? So every time you are getting the power increased of 1 by 3. Right? So if I generalize it, so on, if I generalize kmxxi will be xxi by 3 to the power m or m minus 1. Let's see. Yeah, for 3 it is 2, for 4 it is 3. So it is m minus 1. Right? 1 less power. For k2 it was 3, for k3 it was 2. So for m it will be m minus 1. So this is your km. So therefore the resolvent kernel, therefore r x xi Rx xi lambda will be equal to summation m goes from 1 to infinity lambda to the power m minus 1 and km x xi. And if you recall, your lambda is 1 by 2 in our case. If you look at the equation, let me show you the equation. This is the equation. Here it is lambda is 1 by 2. This is your lambda. This is your lambda. So lambda is fixed at 1 by 2. All right. So you can replace lambda here. Lambda is 1 by 2 to the power m minus 1, and km is x xi over 3 m minus 1. All right. So all you got is x xi is common. Summation m goes from 1 to infinity 1 over 6 to the power m minus 1. Right? 1 by 2 m minus 1 and 1 by 3 m minus 1. So it is 1 by 6 m minus 1. All right. It's a geometric series. The sum of geometric series is, if you recall, what is the sum of this geometric series? This is a geometric series, and if you recall, the sum of the geometric series is 1 over 1 minus r. 1 over 1 minus r. R is 1 by 6 here. This is your sum. Lambda power m, I wrote it before as well. So 1 over 1 minus lambda. So this is 1 over 1 minus 1 over 6. So this is 5 by 6, so 6 by 5. right? So this is equal to 6 by 5 x xi. So this is your resolvent kernel. If this is the resolvent kernel, then what is the final solution? So finally, the solution of a given integral equation is u of x is equal to fx plus lambda 0 to 1 a resolvent kernel and f xi d xi, right? So now we have fx is 5x by 6, this is given to us. Lambda is 1 by 2. Resolvent kernel is 6 by 5x xi, and f xi is again 5x by 6 d xi. Alright, 5 xi by 6. This is fx, so f 5 xi by 6. So 6 is gone, 5 is gone. So you got 5x by 6 plus 1 by 2, 0 to 1 x xi square d xi. So this will give you 5x by 6 plus 1 by 2 x as it is. This is x xi cube by 3, 0 to 1, and this is 1 by 3. So you got 5x by 6 plus 1x by 6. So that is 6x by 6, which is x. All right. So 6x by 6 is. So this implies that your u of x is equal to x. This is your solution basically. All right. This is the required solution. That is x is the solution of the given differential equation. And if you want to prove it, you can prove it like that. Replace x here and see you get the correct answer or not. Right? You replace x here, it will satisfy the equation. So that will prove that this is a correct solution of the integral equation. So this is the method, the very first method we learned for solving the integral equation. It's not difficult at all. Not difficult at all. You just have to remember the steps. That first of all, you need to find k1, k2, k3, so on, and then you have to write the resolvent kernel, and after writing resolvent kernel, you can write the final solution. Very easily simplify it and you will get ux. All right. So I did 2-3 examples. I did this one for Volterra equation, Fredholm equation 0 to 1 as well, right? So you can do 0 to x. It's very easy because resolvent kernel is coming out to be the same every time, right? You can find k1, k2, k3, they are x minus eta. And then I did one of these examples, 2 plus cos x and 2 plus cos eta. So you can do the other two ones as well, x minus eta and 1 plus x square, 1 plus eta square. I hope they will not be difficult for you guys because I have done quite a few examples now. So if you follow the same steps, they will be very easy. So redo this with this x. I did this example from 0 to 1. ठीक है, तो मैंने इसको 0 से 1 के लिए कर दिया. फ्रेडहोम इक्वेशन के लिए आप इसे 0 to x रख के करें एग्जांपल. k1 k2 उसी तरह निकलेंगे, सिर्फ 0 से x तक का फर्क है. ये मैंने वोल्टेरा के लिए किया, kx eta 2 plus cos x 2 plus cos eta वोल्टेरा के लिए, जिसमें लिमिट्स आपकी वेरिएबल होती हैं फ्रॉम t to x. ठीक है, उसके बाद ये मैंने एज इट इज सॉल्व कर दी. ये मैंने फ्रेडहोम सॉल्व की हुई है. ठीक है, ये मैंने सॉल्व कर दी थी आपको इसकी जगह पे. तो ये हमने दोनों एग्जांपल सॉल्व कर ली हैं, फ्रेडहोम की दोनों एग्जांपल्स. इसमें मैंने ये नहीं की, ये वाली सॉल्व की है. तो दिस इज द वेरी सिमिलर टू दिस वन, सो यू कैन डू इट एंड दीज टू. So there are 3 examples left for you guys, and I hope they will not be difficult at all. All right. So let's review this method of successive approximation one more time. So what was method of successive approximation? For Volterra and Fredholm, they are exactly the same. All right. So what you need to do is, this one. This. All right. You take u naught of xi to be f of xi, whatever is given in your function. You take this one, you find u1. Similarly, you replace u1 here, you find u2. You replace u1, you find u3, and so on up to un. All right? But in examples, we don't do that. We directly find k1, k2. Here in the differences, when you take all these differences, we get this recurrence relation, this one. Right? We get this relation that replace k1 here, you will get k2. Replace k2 here, you will get k3. You replace k3 here, you will get k4, and so on. So in examples, in practical examples, we find this kn directly. k1, k2, k3, so on. We don't find u1, u2, u3, so on. We find k1, k2, k3, so on, and after finding that, we obtain the formula for the resolvent kernel, which is this one, right? Resolvent kernel, which is this one. So after finding k1, k2, k3, so on, we replace them here, and this summation thing is your resolvent kernel. We simplify this resolvent kernel, and then this is your final solution. So in this procedure, we explained everything. In this procedure, we explained everything. But in examples, we don't go through every step here. What we do is we find k1, k2, k3, k4, so on from that recurrence relation. All right. After finding that, we substitute k1, k2, k3 in the resolvent kernel formula, which is this one, summation lambda m minus 1 km. This gives us the resolvent kernel, and we replace the kernel. In the original equation, we replace the kernel with the resolvent kernel and find the solution. See, what is the difference between the integral equation and this equation? Integral equation was ux is equal to fx plus lambda a to x kxt ux. So what we did is we replaced u by f and k by r. We do this one and integrate it, we get the final solution of the integral equation. Same thing happens for the Fredholm. You see, this is the Fredholm equation. We do the same thing. We find the same kernel thing, right? We find the kernel, k1, k2, k3, so on. We replace in the formula of resolvent kernel. We find the resolvent kernel, and then your solution is right there. All right? So this was very, very easy. I did, these are 1, 2, 3, 4, 5, 6 examples are given. I did 3 of them. I left 3 of them for you guys. It will be a very good practice and very good exercises for you guys. So do them now, right now maybe. All right, if you have time, do them right now, because otherwise you will forget it later on. So today's lecture summary is the method of successive approximation and nothing else, right? So we basically derived the procedure, the formulas for the solution of Volterra and Fredholm equation by using the method of successive approximation. And in that successive approximation, we used Picard's method. Picard suggested that the first approximation should be fx. All right. So by taking that, we built on that f of x, u1, u2, and u3. So in examples, what we do is we directly find k2, k3, so on. We replace that into the resolvent kernel formula. We find the resolvent kernel, and then your solution is right there. All right, guys. So it was very easy. The method of successive approximation was not difficult at all. You should know the derivation as well. All right, you may be asked to derive these formulas in your quizzes or exams or whatever. So you should know the formulation, that how we got that formula at the end for the solution for the resolvent kernel. So you should know the whole process of finding that resolvent kernel formula. But if the example is given that solve this example by method of successive approximation, then you will not prove the formula. You will find k1, k2, k3, so on, and then you will replace that into your resolvent kernel formula. You will simplify the resolvent kernel and then replace the resolvent kernel in your solution formula, and you will get the final solution. All right, guys. So this is it for today's lecture. I hope you understood it. It was not difficult at all. Do the practice, do the homeworks. That will really reinforce the ideas which you have learned today. All right. So with that, I will take the leave for now, and thank you very much for being with me, and I will see you in next lecture with more on integral equations. So that's it for now. Assalamu alaikum. Allah Hafiz.